Okay, let's take a look at the effect of temperature on reaction rates. All right, so there's a couple things we're going to want to look at in this video. Uh, this is all based on what's called collision theory, which I always thought that term was kind of silly because how do you think molecules are going to react unless they collide? So theory seems to be an odd term to apply there, but basically this is based on an understanding of how molecules collide and what happens when they do. So when they collide, one of the things that's important we'll look at is the orientation, how the molecules are directed toward one another. We're going to look at reaction profiles, which is basically how the energy of the molecules changes during the process of the collision and the reaction. And then based on those properties, we're going to look at how temperature impacts the reaction rates, and the effect of temperature is summarized in the Arrhenius equation, and we'll look at that, of course, and then we'll work a few sample problems using the Arrhenius equation. All right, so let's take a look at a simple reaction. This is one that we had done before. This is nitrogen dioxide reacting with carbon monoxide to form nitrogen monoxide and CO2. Right? And so we're going to look at what happens when these molecules come together. This on the left is nitrogen dioxide. There's kind of a standard color system in chemistry. Nitrogen is almost always blue, oxygen is always red. Carbon is usually kind of gray or black, hydrogens are white, so on and so forth. But anyway, we're going to bring these molecules together, and you'll notice that as they approach one another, right, and get closer, and eventually they're going to collide with each other. And then once they collide, now they're in a position to begin forming a new bond, right? And in order to form CO2, a new bond has to form here between the carbon and the oxygen, and an existing bond here between the nitrogen and oxygen has to break. All right. So as these two come together and pull away, you'll see one bond beginning to form and another bond gradually disappearing. All right. And then eventually we end up with CO2 on this side and nitric oxide on the other side. Okay. All right, so let's look at some of the important aspects of that reaction. All right, one of the important things is the orientation, right? As these came together, I'll use white for carbon here, right? As these come together, the carbon collides with the oxygen on the NO2 molecule, forming a new bond between these two atoms. So that can only happen if these two atoms collide with one another. Right? If the molecules were to approach approach like that, then you'd have this this oxygen and this oxygen interacting with one another, and so you couldn't possibly form that carbon-oxygen bond, right? So this will lead to a successful reaction, and this one won't. And of course, you can come up with a couple other possible ways to come up with successful or unsuccessful reactions. The the carbon could approach from over here and hit that oxygen. That would be just as effective. So that's another possibility for a successful reaction. If the carbon monoxide molecule approaches and if the carbon monoxide molecule approaches, right, and hits here and hits on the nitrogen, then again, regardless of whether it approaches with the carbon end or the oxygen end, that's going to result in an unsuccessful collision. Right? So the takeaway is that in order to react, the molecules have to collide, and that the orientation of that collision is important. All right, now let's look at what happens to the energy of the molecules when they collide. We can draw what's called a reaction coordinate. And you'll see a lot of these in the textbook. And what we're plotting is energy on the y-axis and reaction progress on the x-axis. So for any generic reaction, right, we're going to start with the reactants here, which have some particular energy, right, measured on that y-coordinate, and then the make this a little bit longer, and then the products here. Okay, in this particular case, well, let's go ahead and put in our reactants and products, right? In this case, the reactants are NO and NO2 and carbon monoxide, and our products are NO and CO2. And in this particular reaction, the products have lower energy than the reactants. That's not always the case, but that is the case here. So if we compare the energy of the reactants and the products, this difference right here gives us the change in energy for the reaction. And this indicates that since the products have lower energy than the reactants, this reaction is going to release energy. So this particular reaction is exothermic. Okay, you could, I guess, as long as we've got this here, we'll go ahead and sketch another. You could have a an endothermic reaction, and for an endothermic reaction, the reaction profile would look like that, where the reactants have lower energy than the products, and delta E would be given to you like that. Right? So this would be endothermic. All right. Let's get those guys out of here because we need to talk about something else. Make a little bit of room. All right. So if the reaction were this simple, and the reactants have more energy than the products, then we would expect that during the course of the reaction, things tend to move toward lower energy, so the energy would just decrease like that, going from the starting energy to the product energy. But that doesn't actually happen. If that were the case, then the NO2 and the carbon monoxide would react almost instantaneously, and all of it would be converted from reactants to products in an extremely short period of time. The fact that these processes are slow enough to measure some kind of a rate constant, some finite rate, right, means there's got to be something else going on. And what that is looking at that collision state of the molecule that we showed in that previous slide. If we look at the energies here, our initial substances, the NO2 and the carbon monoxide, are fairly stable, right? And our products, that's not a very good color, and our products are more stable, right? But this has to go through a intermediate state in which there's a bond that's being formed here. So this bond is not completely in existence here. And there's also a bond here that's gradually breaking, right? So this bond is sort of a half of a bond, right? So the NO2 molecule is very unstable because this bond is breaking, and the carbon monoxide is unstable because it's got this new bond forming here. So this whole state in which the molecules are colliding, a bond is forming, and a bond is breaking. This is very unstable, right? Or in other words, this has a high energy. So if we plot the energy across this reaction coordinate, instead of going directly from reactants to products, the energy increases and then comes back down, where the energy here is the energy of the reactants, the energy here is the energy of the products, and the energy here at this peak is the energy of this unstable intermediate. And this species here, which is in the middle of that transition between reactants and products, this species, we call this, oops, I left out an N. We call this the transition state, right? That's the state that's immediately or exactly in between the properties of the reactants and the products. And that transition state is always unstable and has a high energy. So in order for the reactants to go from here to here, they can't go directly from this energy to this energy. They can only do it by going through this unstable intermediate. And that means they have to have a lot of extra energy in order to achieve this high energy state in between. And that amount of energy required to create that transition state here on the diagram is called the activation energy. All right. So that activation energy, we write that with E subscript A, is the energy required to go from the reactant energy up to that high energy unstable transition state. So where does that energy come from? That energy comes from that collision. Remember that as molecules are bouncing around, it's easiest to think of this in the gas phase, but this is also true in solution. As molecules are moving around, they've all got kinetic energy. And when they collide, that kinetic energy can be converted into chemical energy in order to get the molecules up to that high energy state in order to undergo that transition. Okay. All right. And while we're still on this slide, looking at the energy profiles, just want to remind you that an exothermic reaction will look like this, right? It's exothermic, going from reactants to products. Change in energy for the reaction is shown here, and the activation energy is here. Right. For an endothermic reaction, from reactants to products, change in energy is here. The activation energy is here. All right. So the activation energy for the exothermic reaction is a lot less than the activation energy for the endothermic reaction. And that's one of the reasons that exothermic reactions tend to occur faster than endothermic reactions. Also, we'll be looking at this later when we do equilibrium, but we can look at a reaction going from reactants to products, and we can look at that same reaction going backward, right? So if you're looking at the same reaction going in two different directions, if the forward reaction is exothermic, then the backward reaction or reverse reaction would be endothermic, right, for the same reaction. And you can compare how those activation energies change for those two different energy reaction profiles. Okay, so let's look at the effect of temperature on reaction rate. There are two different ways that the temperature is important, and one is, remember from a few chapters ago, we calculated the root mean square. I was trying to say square and speed at the same time. Root mean square speed of a gas molecule, and that was the square root of 3RT divided by the molar mass. Right? We're not going to worry about going back to this calculation again, but I just want to point out that because you've got T in the numerator here, that means the higher the temperature, the faster the molecules are going to be moving. So what that means, and again, it's easier to picture in a gas phase reaction, but the same is true in solution phases. As you increase the temperature, all the molecules are moving faster. And if they're moving faster, they're going to collide more frequently, right? So the first impact of temperature is that at higher temperatures, the molecules have more collisions per second, or the frequency of collisions increases. And that, of course, is going to make it easier for the reaction to happen. Okay. The second part has to do with, again, really from the same section a few chapters ago. You might remember we were talking about kinetic energy of molecules. And if we plotted the kinetic energy of a group of molecules versus the number of molecules with that particular kinetic energy, we get this curve, which we call the Boltzmann distribution. And I'm going to use blue for a cold sample, or cooler anyway. Right. So at, let's say room temperature, 25 degrees Celsius, the Boltzmann distribution would look like that. So most of the molecules have a fairly low kinetic energy, but there are also going to be some molecules out here with higher kinetic energy. But there's a distribution of all of those energies. Now, if we compare that to another sample at, say, 100 degrees Celsius, that's also going to have a distribution with the same kind of a shape, but because the temperature is higher, all of the kinetic energies are shifted to slightly higher values. So at 100 degrees, at 100 degrees Celsius, the Boltzmann distribution might look like that. Now, what that has to do with reaction rates is, you remember that there was that activation energy that had to be overcome by the molecules, and that activation energy comes from the energy of those collisions, right? So if the activation energy is here, and remember we've got kinetic energy on the x-axis, low kinetic energy over here, and higher kinetic energy over here, right? So if the activation energy is here, this represents the minimum energy that a molecule can have and still have sufficient energy to get to that high energy transition state. And if you look at the cold gas at 25 degrees Celsius, the molecules that have sufficient energy to overcome that activation energy barrier is just this small amount here, right? And this would depend on a lot of parameters that we don't really have here, but let's say, for example, for one particular reaction, maybe that's 1% of the molecules have sufficient energy to overcome that activation energy barrier. And if you compare that to the sample at 100 degrees Celsius, those with sufficient energy to overcome the activation energy barrier are these over here, and that might be, you know, perhaps 10%, right? Again, that's going to depend on the temperature, the activation energy, and things like that. But in general, the point is that at higher temperatures, there's going to be a larger fraction of molecules that have sufficient energy to overcome that barrier. And that means a larger fraction of those collisions will be successful in causing a reaction, right? Okay. So if we look back at this, the reasons that the temperature is important Okay. So the first thing is, at higher temperature, the molecules are all moving around faster, and as they move faster, they're going to collide more often. So there's a higher collision frequency. And the second reason is at higher temperature, all right. Sorry, I'm kind of a slow writer. All right. So the second reason is, at higher temperature, a larger percentage of the molecules will have sufficient kinetic energy to overcome that activation energy. So more collisions, and of those collisions, a larger number of those collisions will be successful in creating a reaction. All right. So we can take those two things together and put that together, and we get the Arrhenius equation, which looks like this. K, that's the rate constant, equals A times e to the negative EA over RT. This is the activation energy, ideal gas constant, and temperature. So K is our rate constant, and we want to be thinking about units. And the units on the rate constant are going to vary depending on the order of the reaction, right? As they have previously. Right? So, a zero order reaction, you have units of molarity per second. A first order reaction has units of reciprocal second. A second order reaction, units of reciprocal molarity second, and so on and so forth. All right, so K is our rate constant with units that depend on the reaction order. A is called the frequency factor. It's sometimes called the orientation factor, or more generally, I think it's kind of funny, the pre-exponential factor, which pre-exponential just means that it comes over here before the exponential. This is the exponential part, so that's the pre-exponential part. Means absolutely nothing chemically or physically. It's just explaining where it is in the equation. But anyway, so A is the pre-exponential factor. I often call it the frequency factor. A lot of other people do. If you look at the units, you'll see that this part here, E raised to some power, has got to be unitless because E doesn't have any units. So you take something unitless, raise it to a power, it's still unitless. So if E doesn't have any units, but K does, then the frequency factor has to have same units as the rate constant. So the frequency factor units on that will vary from reaction to reaction. EA is the activation energy, and here I've written joules per mole, right? When you put this into the equation here, R has units of joules, so in order to get everything to cancel out, the activation energy also should have units of joules, okay? So I think joules per mole is essentially correct there, but when people cite activation energies, they usually give the units in kilojoules per mole. So you'll see activation energies in kilojoules per mole. Just remember that you need to change it to joules before you do the math. R is the ideal gas constant. And remember, there's one ideal gas constant for PV equals nRT type problems, and another one for things more related to physics, right? The two R's are the same, they just have different units. The number is different because the units are also different, right? But physically they mean the same thing. Anyway, my point is, when you're doing this problem, make sure you're using this R and not the one that's in liters atmospheres per mole Kelvin. All right. And then T, of course, is the temperature. And what do you need to do to the temperature all the time, particularly if you're working with the ideal gas constant? Temperature has to be in kelvins. So make sure you've got your temperature in kelvins when you're using the Arrhenius equation. All right. Okay, so let's do a simple problem. A reaction with an activation energy of 42 kilojoules per mole has a rate constant of 4.5 times 10 to the minus 2 reciprocal molarity second at 25 degrees Celsius. What is the frequency factor for the reaction? So first question, which doesn't really have to do with the math, is what is the order of the reaction, right? And if you look at the units on the rate constant here, right, units of reciprocal molarity per second means that the reaction is second order, right? We don't actually need to know that to do this problem, but just wanted to mention that, kind of a review, right? So to solve this, we're going to use the Arrhenius equation that we just had. K is equal to the frequency factor times E minus EA over RT. Okay. So we need to let's put some things out over here. Need to get some things into the proper units. Our activation energy is 42 kilojoules per mole, but remember that 1 kilojoule is 1,000 joules, so this is 42,000 joules per mole. Okay, and I may have to erase this to make room for the problem, so make sure you've got that down. The temperature also has to be in Kelvin. So to get from Celsius to Kelvin, we add 273. That gives us 298 K. All right, so let's go ahead and put this in here. Let's see. I'm not going to put units. I'm not going to put the value in for K yet, just because it gets a little bit messy. I'm going to focus just on the exponent on the right for now. That's A times e to the. Put this whole thing in here. Our activation energy is 42,000 joules per mole. So we've got 42,000 joules per mole. And in our denominator are 8.3145 joules per mole Kelvin, and our temperature is 298 Kelvin. All right, so we'll check our units. We've got Kelvin here, which cancels Kelvin here. We've got joules per mole here, which cancels joules per mole there. So our exponent is unitless. That's important. Exponent should always be unitless. All right, and let's also not forget our negative sign here. We put that in the calculator. That gives us e to the minus 4.35. Nope, oops, sorry about that. Erase that. I'm getting ahead of myself a little bit. That gives us e to the minus 16.95. Oops, I forgot my a here. All right. So K is equal to A. Here, put this in your calculator. E to the minus 16.95 is 4.35 times 10 to the minus 8. Okay. And I guess just a little word of warning here. When you're doing problems like this, when you've got E raised to some large value, very, very small rounding errors in here result in very, very large errors here. Okay? So if two different people work this problem, the answers may end up varying by, well, I guess I would say the difference in answers are going to be larger than you would normally expect, because the rounding errors are just going to be a lot larger. Anytime you've got these exponents like this, the rounding error is going to get magnified. So if you try to do one of these problems two different ways, and your answers are different by about, usually you would expect them to be the same to within at least 1%. In this case, your answers may differ by 3, 4, 5%, something like that. Don't be alarmed if you do the equation a couple of different ways and you get slightly different answers. It's probably just due to rounding error because of that exponent. All right, let me clear a little bit of space and we'll continue with this. All right, so this is where we were before. We want to solve for A, so we can just divide both sides by 4.35 times 10 minus 8. I'm going to go ahead and put the value in for K at this point. K, remember, if you look up at the top of the page, right, is 4.5 times 10 to the minus 2 per molarity second. Divide both sides by that part we have on the right, 4.35 times 10 to the minus 8, and that's unitless. right? That equals A, which is 1.035 times 10 to the 6th per molarity second. Okay. And I would go ahead and keep that number handy for if you're going to do follow-up questions. Keep that number handy so you don't round off too prematurely. But if the problem was just asking you for A, in this case, given the data here and here, you'd want to round that to two significant figures, and you'd call that 1.0 times 10 to the 6 per molarity second. And again, those units are important. Okay. Okay. Let's do another fairly simple one. All right. So for the same reaction, what would the rate constant be at 35 degrees Celsius? Right. Well, at 25 degrees Celsius, it was 4.5 times 10 to the minus 2. We said before that reactions increase with temperature. So at 35 degrees Celsius, the rate constant should be a little bit higher. And what we usually find is that rate constants double with about every maybe 5 or 10 degrees change in temperature, right? So if we go from 25 to 35, we can expect it'll maybe about double, maybe a little more than that, maybe a little less than that, but somewhere in that ballpark. So we might look for 9 times 10 to the minus 2, right? My point in saying that is just that it's not likely to be 4.6 times 10 to the minus 2. It's not going to be a teeny tiny change, and it's also not going to be 17 times 10 to the minus 2. It's not going to be a gigantic change like that, right? So maybe 9 times 10 to the minus 2, something like that. All right, let's go ahead and do the calculation. Again, we'll use the Arrhenius equation. Okay. And here we're just solving for K on the left-hand side, so that's pretty easy. We don't have to do any algebra here. We'll just put in our values. A we calculated before is 1.035 times 10 to the 6 per molarity second. E, and then our activation energy is 42 kilojoules per mole, or 42,000 joules per mole. All right. Divide by R, 8.3145 joules per mole Kelvin. And then the temperature, remember to convert from Celsius to Kelvin, we add 273, and so this gives us 308 Kelvin. Okay. And again, check our units. Those kelvins cancel. Joules per mole cancel. And then if we take everything in that exponent up there, run that through the calculator, it gives us negative 16.40. And just do that in the calculator. E to the minus 16.40 is 7.538 times 10 to the minus 8. And so K is 7.8 times 10 to the minus 2 per molarity second. Okay. Let me rewrite that a little better. All right. Now, when you're working through this, remember a little bit of rounding error here can result in a large error here and a large error over here. So if you kept more or fewer digits in your calculator here, you might have gotten 17.6 or 17.9, or I mean 7.6 or 7.9. Your answer here may be a little bit different than mine, but it should be pretty close. Okay, the two calculations that we just did, we're looking at the Arrhenius equation. We're solving for K in one case and solving for A in the other case. Those are both pretty simple. We didn't have to do any fancy math with them. But what if we're trying to solve for the activation energy? With the activation energy up there in that exponent, it can get a little bit tricky to get that one. So in order to solve for something that's in the exponent, we're going to do the same thing we've done a whole bunch of times in the last couple of weeks. We're going to take the log of both sides. Right? So take the log of the left, we just get natural log of the rate constant. On the right, we've got two things that we're multiplying, right? A times e to the minus ea over rt, and the log of a product is the sum of the logs, right? So we get log of a plus natural log of e to the minus ea over rt, right? And of course, natural log of e to the ea over rt, those two things are inverse functions, so they essentially just sort of cancel out. So we get natural log of a minus ea over rt, and I'm going to do two things here. First, I'm going to switch the order here. Okay. And then I'm going to do something really, something that looks kind of weird with this fraction here. Since we are looking at the effect of temperature on the reactions, we want to try to isolate temperature here. So I'm going to rewrite this as negative ea over r times 1 over t plus natural log of a. Okay. And that looks a little bit weird, I admit, but this now hopefully is getting familiar to you, right? If we plot natural log of the rate constant on the y-axis, and instead of plotting the temperature on the x-axis, plot the reciprocal of the temperature on the x-axis, then this will give us a straight line in the form y equals mx plus b. Okay. So we should get a straight line like that, and see that the slope is equal to negative ea over r. Right. So I'm going to clear a little bit of space over here. All right. So you can see from this equation that the slope is negative EA over R. So if the slope is negative EA over R, then EA is negative slope times R. So if we're solving for the activation energy, we can just create this plot, and the activation energy is the negative slope times R. Notice when you do this, when you create this graph, the slope here is always going to be negative, but activation energy by definition is going to be positive. Okay? And if we extrapolate this line here, right, where this interacts here, this y-intercept is natural log of the frequency factor. Okay, let's give this a try. All right, here's a problem. The rate constant data here were collected for a reaction. What are the activation energy and the frequency factor for this reaction? And also, what would the rate constant be for the reaction at 60 degrees Celsius? Okay. All right, this has everything in it, right? Solving for all different variables, solving for EA, activation energy, frequency factor, and the rate. So if you can work through this one, you should be able to do just about everything. All right, to get the activation energy, we need to get that plot, right, of 1 over t versus natural log of the rate constant. So we're going to take all of this data and expand our data table a little bit. We'll make a column here for temperature in Kelvin, and the first one, 25, of course, to get to Kelvin, add 273, so this would be 298 Kelvin, and the next one would be 303 Kelvin, so on and so forth. Okay? But remember, on that x-axis, we don't want temperature, but rather reciprocal temperature. So we make another column here. We take the reciprocal of each of these numbers, and you can do that in your calculator by typing 1 divided by 298, 1 divided by 303, so on and so forth. Or you can type in 298 and hit your reciprocal key. But in any case, you get 0.00336. And notice that the units on these are reciprocal Kelvin, which is kind of a weird unit, but that's what it is. And for the next one, 0.00330, reciprocal Kelvin. And then finally, we also need the natural log of the rate constant. So to do this, you just take rate constant right here from the table and put it in your calculator, take the natural log of the rate constant. And when you take the log of something, you lose the units. So this column here is unitless. So you get minus 2.17, minus 1.91, so on and so forth. Okay. I'm going to show you my table on the next slide, but you can go ahead and calculate them all if you'd like, or you can just wait until I show you what I got. Here they come. All right. So when you finish calculating that, you should have a table that looks like this. And if we put all of this into a graph, we should get a straight line that looks like that. So here's the graph. I trimmed the table down a little bit just to show our x coordinate and y coordinate. But here's our graph, and indeed we've got a straight line, which is lovely. That's just what we wanted. I'll point out something on the x-axis, which is a little bit counterintuitive. Since you're taking the reciprocal of the temperature, this is actually high temperature here, right, with the larger rate constant values, and low temperature out here with the lower rate constant values. Okay. That doesn't matter most of the time, but it's helpful just when you're looking at the graph, because sometimes it can be a little bit weird to see the high temperature values on the left and lower temperature values on the right. All right, so let's go ahead and use this to determine our activation energy and our frequency factor. Okay, so the first way that we can get the activation energy is by finding a couple points on this graph here, say, and here. All right. Okay. So if we look at the y values, I'll take this as 0.2, and this is 0.1. All right. So our y value, we've got negative 2.0 minus negative 1.2, so that's going to be plus 1.2. And in the denominator, you probably can't read these numbers here, but if you make your own graph, you should be able to see these numbers, and this is 0.00332 reciprocal Kelvin here. And if we look at this one over here, this is minus 0.00315 reciprocal Kelvin. Okay, kind of weird, right? The numbers are a little bit weird here. In the numerator, minus 2 minus 1.2 is minus 2 plus 1.2. So this gives us negative 0.8. And in the denominator, I got 0.0 0.000170 reciprocal Kelvin, and put that in the calculator, and I got 4706. And the units, we've got Kelvin here in the denominator of the denominator, so the slope is and also, oops, I almost forgot this negative sign, negative 4706 Kelvin. Okay, so the slope that we got here was negative 4,706 Kelvin, but that's not our final answer. Remember from a little bit ago, we said the activation energy is equal to negative slope times R. So the activation energy is negative 4706 Kelvin. Oops. What did I do there? See where I made my mistake? Our activation energy is negative 4706 Kelvin times 8.3145. I'm kind of running out of room here, sorry, joules per mole Kelvin. Okay. So the kelvins cancel and the negatives cancel, and for the activation energy I got 39,127 joules per mole. And like I said, people generally report activation energies in kilojoules. So our activation energy is 39.1 kilojoules per mole. All right, terrific. All right, I'm going to get through this quickly, because we've done this with all of the other topics we've done. Anytime you've got a graph and we're calculating a slope, you can get the answer by looking at the graph and finding a couple of points, or you can just pick a couple of points here on the table, and there's our delta x. Excuse me, there's our delta y, and there's our delta x. So we can do that. Okay, so I ran through this, and just choosing a couple of values here, and chose that pair, and plug those in to calculate delta y and delta x. And when I did that, I got a slope of negative 4,625 kelvins, same units as we had on the last page, as it should be. And then remember that that's the slope of the line, that's not the activation energy. Activation energy is negative slope times r, so that's negative 4,625 Kelvin times the ideal gas constant. And when I did that, I got 38,454 joules per mole, or 38.5 kilojoules per mole. All right. So slightly different, a little bit of difference in rounding in those two, as to be expected, but approximately the same value in both cases. I'll just tell you that I generated this data set with the calculation for which the actual activation energy is 39.2 kilojoules per mole. So we'll go ahead and use that value for our subsequent calculations. But you could have used this one or the one you got on the last page. I'm just trying to decrease our rounding error and keep everything as consistent as possible. Okay, so next we want to calculate the frequency factor, and we can do that by starting with our Arrhenius equation. So that means you can put some numbers in first and then do the algebra, or you can do the algebra first. Either way. And you should be able to calculate this using any of those, any pair. If you go back to the original data set, choose any rate constant and temperature combination, put in the activation energy of 39.2 kilojoules per mole, or 39,200 joules per mole, right? Put any of those in there and you can calculate the frequency factor. I'm going to go ahead and erase this, clear a little bit of space, and I'll do that. Give me just a minute. All right, so when I did this, I just went ahead and chose the first data set at 25 degrees Celsius. So I put in the initial rate, the rate at 25 degrees Celsius, that's here, and 25 degrees Celsius, 298 Kelvin, put that in there. And when I did that, this whole thing here came out to be 15.8, right? So the denominator became e to the negative 15.82, which is 1.35 times 10 minus 7. I took the rate constant and divided by that. I got 8.47 times 10 to the 5 per molarity second. So that's our frequency factor. Now, I'll mention there's another way that you could do this. Right? If you've got, it'd be hard to do this with pen and paper, but if you've got this in Excel or some other program like that, or calculators can do this too if you know how to do this in your calculator. If you've got a graphing calculator and you know how to use it, you can put the values into your calculator and get a graph and calculate the line of the graph. And we did that with Excel. They gave us y equals negative 4714 times x plus 13.653. Right? This part here is the y-intercept. And remember a few slides ago when we were talking about linearizing the Arrhenius equation, we said that that y-intercept is equal to the natural log of the frequency factor. So to solve for the frequency factor, you just take e raised to the power of both sides. And of course, e to the ln a is just a, right? So a is e raised to the power of this y-intercept, which is e to 13.653. And if you put that in your calculator, you get 8.5 times 10 to the 5. When you take a log of something, you lose the units. So when you go back in the other direction, the units don't come out automatically. You just have to put them in based on the units of the rate constant. But that's kind of nice that using those two methods, we got the same value for the frequency factor. All right. And then we've just got one more fairly quick thing to do, and that is calculate the reaction rate at 60 degrees Celsius. And as we said before, the reaction rate keeps increasing with increasing temperature. So at 45, it was 0.309. So at 60, it should be higher than that, maybe 0.5, 0.6, 0.7, somewhere in that ballpark. Okay, so we can do this. We're just solving for the rate constant, so we can just use the Arrhenius equation as written without any algebraic manipulations, right? So our rate constant is this frequency factor and for this exponent up here, put in our activation energy per mole, 8.3145 Kelvin. And then our temperature, right? We've got to convert this to Kelvin, and 60 degrees Celsius. If we add 273 to that, we get 333 K. Apologize for the handwriting. I think that happens when I get tired. All right. And this whole collection of things up here, check all the units. The units cancel out, and this whole thing gives us negative 14.16, and e to the negative 14.16 is 7.1 times 10 to the minus 7. And of course, this is unitless over here. And so we get a rate constant of 0.603, which makes sense. That's a good number. All right, wonderful. All right, we did a whole bunch of calculations in that one. That video was kind of long. I think that's the most mathematically complicated topic, definitely in the whole kinetics chapter, maybe in the whole semester. So work through those slowly, practice those. There are several examples in the study guide, so work through those and make sure you're able to do them. So we talked about molecular collisions. We talked about the importance of orientation, and the orientation shows up as that orientation factor in the Arrhenius equation. The more specific orientation that you need to get the reaction to go, the lower that A value is going to be, because that's going to make the reaction more difficult if you need a very, very specific collision orientation. Right? We also talked about that high energy intermediate for the reaction. That high energy intermediate is called a transition state. And in order to get to that transition state, the molecule has to gain some energy. That energy is called the activation energy. People sometimes call it the activation energy barrier. Right? And temperature increases the rate of the reaction for two reasons. One is because at higher temperatures, the molecules are moving faster, and so they collide more frequently. The second reason is at higher temperature, the molecules have higher kinetic energy, and so more of those collisions are going to have sufficient energy to overcome the activation energy barrier, or those two factors there dealing with the temperature. And you can combine that information to get the Arrhenius equation. This is an important equation that you should know. So I've got the Arrhenius equation here, and you can linearize that. The math here is a little bit funky. Again, it looks a little bit complicated, but the result is that if you plot 1 over temperature, reciprocal of the temperature on the x-axis, and the natural log of the rate constant on the y-axis, you get a straight line, and the slope is equal to negative EA over R. Okay. All right. Have fun with those and practice them, and we'll be back with one more topic in kinetics, and then we'll move on to our next section.